equations for simple harmonic motions. We have displacement as a function of time, velocity as a function of time, and acceleration as a function of time. So that means we can describe the displacement, the velocity, and the acceleration of this mass spring system, for example. So that it has once we know the period, we know the frequency, and we know the omega. So this all is described using this formula. Alright, so it can oscillate between 2 points A and negative A. So it is nice, can be described. This 1, 2, 3, 4. These 4 quantities can be described by using these equations. But so far in this equation, there is no involvement of the spring constant and also the mass. So we want to know what is the relation between this spring constant, mass, and these other parameters. So to proceed with that, again we refer back to the circular motion. Okay, since the simple harmonic motion is a projection of a circular motion, Okay, consider again this point Q, and this Q circulating around, and this is the projection of this Q. So that means as this moves, this also oscillates in one direction. Okay. So review again the lessons about circular motion in mechanics. So this, if this Q circulating around a circle path, it has an acceleration toward the center. Okay, this is the acceleration, centripetal acceleration, and it also have a tangential velocity. So this tangential velocity always change with time. Okay, and it also rotates with angular speeds omega. Alright, so and then the distance from the center to the path is radius, the radius of the circle. Okay, this is r. Okay, so from the mechanics circular motion, we have the tangential velocity is equal to the angular speeds times the radius. Okay, that is the formula. And then from the previous video, this VQ is actually the maximum value of this circle simple harmonic oscillator. So VQ and Vmax is same thing, same value, not something but same value. It takes the same value. And omega is the angular frequency of this simple harmonic oscillator, and R is equal to A. Why R is equal to A? Because from here you see that the radius is also equal to the amplitude of this simple harmonic oscillator. So this is radius, so you see this is the same length. Okay, so we have here Vmax equal to omega A. So we can put this Vmax equal to omega A into our equation here, so that we have a negative omega A sine omega t. How about the acceleration? So from the circular motion, acceleration of the circular motion is equal to omega r square r. Okay, the difference is just this is omega square. Okay, r is equal to A because we know it before. Okay, and then we can replace this into the our equation here. We have a detail, this is equal to omega A square cos omega t. Okay, now we still want to have the relation between these three. Still we can't see it now yet, but we continue to A equal to minus omega square A cos omega t. Okay, so we rewrite again this A and this A. So we rewrite again. Okay, so this is omega A cos omega t. So notice that this A cos omega t is also equal to this x. This is equal to x here. Equal to x. So we can rewrite back this is A equal to negative omega squared x. So you can make another form of equation. Okay, so the acceleration as a function of time equal to negative omega x. X is a function of time. This is x a function of time, not x multiplied by t. It's a function of time. Okay, so the maximum value of acceleration happen if the x equal to a. That means the acceleration is maximum at here, right, and here, 2 points of maximum displacement. the acceleration is maximum here, so that the force is also maximum here and also here. Okay, so we can I put here plus negative and positive because acceleration can have maximum value here and here. So the maximum value is equal to omega squared a. That means I just take an absolute value. So this is one thing. Now again, refer to the first lesson about the acceleration and the displacement, the relation between them. So you have this equation before. The x is amplitude. That means if we want to find the maximum acceleration, we put it x equal to plus minus a here, and we have this absolute value for acceleration is a over ma. Okay, so you see both they are separated, but now we want to combine. We want to compare between these two, mx and max, a and a. So from here we can get that omega squared equal to k over m. Okay, so we have this relation. So this relation will relate k, spring constant, m, and these three gangs. I said gangs. Okay, so these are related between these two and these two, because this equation doesn't relate with this k and m, but now we have all together is connected by this equation. Okay, so when you expand omega equal to 2 pi over t, right? And from here, what you can get is that the period of oscillation depends on the mass and also depends on the spring constant. So what is the implication of this equation? This relation is that if we look carefully to the case of, for example, baby swing, right? So you have spring and you have a baby. So if this baby, of course, the baby grow and the mass is increasing. So when the mass increase, what happened? The period is also increased. That means the oscillation becomes slow as the baby get older, because the mass increase, the period become longer, right? So how to actually to make the period shorter period? So to have a shorter period, we have to increase this k. That means we have to use the more harder spring, or spring with a more hard k. So this will relate what is happening between these three parameter: mass, spring constant, mass, and also the period of oscillation.